Hi everybody, so we're going to pick up with our example problems that we're doing with Archimedes' principle. So we're looking at two examples where, if you looked at the end of the first tutorial, we had situation A and B where we have something that doesn't sink or rise. In other words, it turned out that the densities had to be the same because the weight of the water displaced was equal to the weight of the object. And then when we put another body in that had a higher density, essentially what we have, it sinks, is simply because the weight of the object, mg, which is rho of the object, v of the object, g, is greater than rho of the fluid, g, v, which is the same value, times g. So in other words, these are the same for both cases because the volume of the water displaced is the same as the volume of the object, so it just turns out to be comparing the densities. So another aspect we can look at is what if we've got a body that floats to the top, okay? So in other words, we put a third body in there and its density is less than water, so it's going to float to the top, and we want to understand how much of it is underwater, okay? So again, I just want to make sure what this diagram is showing here. We had something here initially, and then we had a buoyant force. We have the F of G of the object, and in the initial case, when it's underwater, the buoyant force is greater than the gravity. So it's going to accelerate up. If we ignore water resistance, drag on it as it goes up, then we can apply the second law and calculate acceleration, but that's not our goal here. So it goes from this state to this state, so at some point it's floating, but it's not sitting on top of the water. And so we can easily understand what's going on here by understanding when it floats such that they're in equilibrium. Okay, so we have F of G. Now, what we want to make sure we're very clear of in solving this problem is that the volume of the part that's underwater is different than the volume of the entire block. So if we do use the law of the balance forces, we can say F of B is equal to F of G, right? Okay, and this is the density of the fluid times the volume. I'm going to put G here, and I'm going to put a V, a D here for displaced, right? That's this volume right there. So it's not the volume of the whole object, whereas the force of gravity is the density of the object, G, times the volume of the whole object. So this works out very nicely. We can see that the G's cancel out once again. And if we're looking at what ratio of the volume of the object is underwater, in other words, what is V of the D to displaced versus V of the object, that's nothing more than the inverse of the densities of the object relative to the fluid. In this case, it's 2/3, because that's the information given. And so 67% of that object is going to float underwater, which makes sense. The closer the density of the object is to the fluid, the more it's going to be underwater, and the reverse of that is also true. If it's a very low density comparatively, most of it's going to be floating out of the water. All right, how much external force must be applied to the object to just go underwater? So now we want to go from the situation, if I go diagonally from this, we want to push it underwater and sink. Okay, well that's pretty simple. The applied force, right, if we do an FBD, which is what this is right here, we still have F of G, we have the buoyant force. And note that the buoyant force is going to go up as we push it underwater because we're displacing more volume. Okay, so this is, if we work out the forces, that's just nothing more than the weight of the object minus the new buoyant force. I'm just going to put a prime there to indicate it's going to be a different buoyant force than the one above. So this just simply is the density, right, times Vg on that one. So that's a pretty straightforward. Okay, I alluded to this before. If I put this underwater, what's the initial acceleration? Well, by the second law of motion, A is F net over m. And once again, F net is going to be the buoyant force minus the weight of the object, because we know that they're bigger because the relative densities. So I'll make this a little bit smaller. And divided by the mass of the object. Okay, so now we want to simplify this in terms of the densities. Those are the givens. So once again, the difference between the two is nothing more than the density of the fluid minus the density of the object, G times V, right, divided by the mass of the object. Now I'm going to transform the mass of the object to the density of the object times the volume of the object. And what we can see here is that the volumes cancel out. And so I could split the numerator up, but I'm not going to. So we can express, the point is we can express a lot of these mechanical solutions in terms of just densities and G. A lot of times volume cancels out. So be mindful of transforming mass into a density. Okay, rank the buoyant force acting on each object. And I've kind of talked about this in a previous problem. So here we just have an object floating. Here we have an object that's being pushed down. It's the same object. Then here we have a different object that is more dense. Okay, so I'm just going to shade this in to indicate that this density of C is different than the density of A and B. A and B we're going to assume are the same object, even though it's not made explicit here. Okay, so how do we approach this? Well, we can use Archimedes' principle. We can say the buoyant force is rho of the fluid, which is the same in all cases here. Even though the densities of the objects are different, that doesn't factor in here. G, which is the same for all, and then the volume, okay, and the volume displaced. So in this case, the volume displaced is the same, so B's got to equal C. And since there's less volume displaced here, that's got to be the least of them. And so even though we have different density objects, we have different amounts submerged, you got to look at it from the Archimedes principle and make sure you're focusing on the fluid density, not the object density, and the volume that is completely displaced. All right, let's continue on. Okay, this is something I would normally want to do in class. It's a really cool idea where we're going to use just a balance, an electronic balance, to find the density of a material, an unknown material, in this case, some object here. Normally, if you define density, right, you'd find the mass using the scale, and then you'd find the volume using either geometry, if it's a nice, simple shape, or you could do a water displacement method with a graduated cylinder that you learned back in middle school or chemistry. Here, we're going to show you how we can figure out volume just by using a scale, knowing that we're working with water and Archimedes' principle. So let's say I do this, okay? So we pretend I have a mass, so it's maybe an aluminum mass, that I have on a string that I put on the balance, okay? And it reads, and I just have this example here, 56.8, let's say, grams. Now what I'm going to do is I'm going to take a beaker of water. Now I'm over to part 1, and this is some water in there. I'm going to tear the balance so it doesn't register the beaker or the water, and then I'm going to submerge partially this guy in there. And I'm going to ask, what's the balance going to read? In other words, is it going to read anything at all? So take a minute, pause right here, and ask yourself, will this balance register the fact that this is partially submerged? This is being supported, right? That's hanging from something or somebody's holding on to it. Okay, and the answer is yes, it will register something. Why will it register something? Because the part that's underwater displaces water, and it displaces the weight of the water that's displaced, which is equal to buoyant force, will register right here. Okay, so I know this is going to seem strange, but I'm going to put it's going to be less than 8.9. All right, grams, and that will, I think, become a little bit more apparent in a minute. But it reads something. The 8.9 comes from how much I submerged it, the material itself, or actually the volume of the material itself, not the actual density. Okay, now instead, let's go from this situation, partially submerged, to fully submerged. Okay, what do we expect the reading to be? Well, if this was less than 8.9, all right, this is going to be greater than 8.9. In fact, it is, in this particular case, 8.9 grams. The point is it's going to be greater when it's fully submerged than when it's partially submerged. But that 8.9 is going to be important relative to this to ultimately find the density of the material. So again, why does this read higher mass? And the mass is a proxy for force, okay? Because we just multiply everything by G and we get the actual buoyant force. because it's simply displacing more liquid. So since it displaces more liquid, in other words, it raised the level, let's say this much, the scale is going to register that. Note the scale is not registering the mass of the object because the mass of the object is being supported by the water and not the scale itself. Okay, now here is the more interesting one. Let's say now we rest it on the bottom. Okay, what's it going to register? We know that when it is sitting on a scale like this, it's 56.8. When it's partially submerged, it registers a fraction of that. So what's it going to read when it's on the bottom? So pause this and then reflect on your answer. Okay, so the reading on this is 56.8 grams. In other words, it's reading the mass. Now, the temptation to say is, be honest with you, what I would have said initially is it's going to read something less than the mass, the full mass of it, because we have a buoyant force, right? There is a buoyant force acting on it, even though it's resting on the bottom. And of course, there is its full weight, which again is what the mass is reading. So why is there not this difference between the two? Because you got to understand that we displaced a lot of water, which is pushing down, which is still reading. In other words, these are offsetting, still giving us the full mass. Okay, so that's not obvious. Now, let's get back to our original goal here. Let's figure out the density. So the density of this is going to be the mass divided by volume. So we know that the mass is 56.8 grams, whether we read it directly sitting on the bottom of the cup or an initial one. So where do we get the volume? Well, we're going to get the volume from this measurement here. Okay, so let's see if this makes sense. We have this thing resting, something is supporting the string, which is different than this one where it's on the bottom. So we have some tension up, we have some buoyancy up, and then we have the weight down, right? I'll call that Fg. Okay, so what is this reading? Well, that's reading nothing more than the buoyant force. Okay, in other words, it's reading how much water we displace, which is the buoyant force. Now, how does it help us get volume? Well, I'm going to go over to the side here. The buoyant force we know is rho times the rho of the fluid, g times the volume displaced. Well, what is rho? Well, since we're putting in water, and if I do things in grams per cubic centimeter, that's 1. And if I take 1 times g, then what I see then is, or if I divide by g, I see the volume is nothing more than the buoyant force divided by g, and that's nothing more than the mass of the scale reading. Okay? In other words, the volume is this 8.4 grams because of the fact that we're using a fluid that has a density of 1. It's a really neat way of getting the equivalent volume. So I have 8.4 cubic centimeters here, and I divide 2, and I've got a very accurate density, assuming my scale is reading correctly. So that's kind of a cool problem. All right, so let's look at a few questions. Once the object is fully submerged, how does FB change with depth? And the answer is it does not. Okay, because FB is ultimately due to pressure differences, and the pressure differences go by the differences in height, which isn't changing. In other words, the height of the object. So as it drops, there's more pressure on the bottom, but there's also proportionally more pressure on the top, but the difference stays the same. If the object replaced with an object of the same volume but greater mass, how would FB change? It would not. Because the buoyant force depends on the volume of the fluid displaced, which is dependent on the volume of the object. The density of the object or the mass of the object is irrelevant. How could the density of the object be determined using the electronic balance? Okay, that's what I talked to you about before. Basically, what it boils down to, the mass of the object divided by, and that's not quite right, but I'm going to just kind of put this in parentheses, the buoyant force. Because the buoyant force, when it's supported by the string, is equivalent to the volume because of water. Okay, so I'm going to stop there for now. Try these problems, and it looks like I don't have answers. I will try to give you solutions to those in a little bit, either through another tutorial or through a PDF.